Hello everyone, welcome. My name is Damien, and we're going to have a quick session about the basics of implicit differentiation and related rates. First, let's consider this function. Something like y equals to 3x cubed plus 5x squared, make it look like plus, and plus 2x plus 7. It's a very generic, very basic kind of a cubic function, and it's got two variables. So this is the type of function with two variables that we're most familiar with, right? So as you have learned from previous lessons, this function is easily differentiated using the differentiation rules in the condition that the rate of change we are looking for right now is of the change of y in terms of the changes of x. So let's differentiate it. We can use the y to y prime notations, but today we're going to be using the Leibniz notation in order to emphasize the fact that we are differentiating the values of y in terms of the changes of the values of x. So, in order to do that, we're going to say d dx of y. We're differentiating in terms of x. For y, doing that d dx for 3x cubed plus d dx for 5x squared, d dx for 2x, and d dx for 7. Okay, as we already know, the constants are gone, and this one, y is going to be differentiated, and it's going to be gone with only leaving behind the coefficient of 1. But at the same time, we're going to be differentiating y in terms of x. So we're going to have to say there was a y differentiation in terms of x. That's what that would mean. And if we look at over here, we just simply differentiate this using the differentiation rules, and it becomes 9x squared, and we don't have to write anything else because this was in terms of x and x to begin with. So this one will become 10x, and this will become 2. It's really simple, it's really easy, but we're not always going to be given readily differentiable functions like this that's already solved for y. So let's consider some funky functions other than this. First of all, let's clear the board. And this time we're going to have something like this. 3 equals to x cubed plus 2y squared half z to the power 5, something like this. Sure. So this one, well, it's not even solved for y, and these are 3 variables, and as you can tell, it's pretty random. Okay. So if we were about to differentiate this, how are we going to be doing this? Well, the thing is, we're going to be doing the exact same thing. Right now, we don't have specific things to talk about, so let's just differentiate in terms of x. So let's do the same thing as before. d dx 3 equals to d dx x cubed plus d dx 2y squared plus d dx z to the power of 5 over 2. Okay, so let's differentiate. Constants always just gone, is 0. Right now we're doing the rate of change of x value in terms of x, so we don't have to write anything down. We just differentiate 3x squared, and then we move on to the next one. So this one, y, is something that we saw before as well. So what do we have to do? First of all, we're going to have to differentiate this using the differentiation rule. So this will become 4y. Then what? Our d dx is going to be left with, okay, so we have differentiated y in terms of x, and we have to denote that here to create the link between x and the y. So that's what we have. Similarly, when we're doing differentiating the z, same thing's going to happen. 5z to the power of 4 all over 2, and we're going to have dz over dx. Now, we're not looking for a specific function or a specific value, so that would suffice at this point. So the important note to take home from this is that when we are differentiating other variables using the terms of one variable, we are relying on the relationship of the variables and how they change together. Therefore, their rate of change in relation to the rate of change of x needs to be stated like so, dy over dx and dz over dx. And that is what it means to differentiate implicitly. So this solution right now, it might be a bit confusing and arbitrary, so why don't we use a actual related rates question in order to testify how our implicit differentiation works. Okay, the board's cleared. Let's get started again. So this is the question that we're going to be working on. It's much smaller than I thought on the screen. I hope it's, you guys can read this. But it says, a spotlight on the ground shines on a wall 10 meters away. A man 2 meters tall walks from the spotlight towards the wall at a speed of 1.2 meters per second. How fast is his shadow on the wall decreasing when he is 3 meters from the wall? So, there are actually quite a bit of information for this question, so let's start writing everything down. The first thing I like to write down is the actual value that we're looking for, and that will be how fast his shadow on the wall will be decreasing over time, so I can see that as dy over dt. Now, we don't have the variable t, but I have to introduce it in here because the idea of changing of y over changing of time. So that's what we're looking for. Then if we read further, the man is going to be 2 meters tall, and that's not going to be changing, so I don't think I'm going to write anything down about that. Over here, he's walking at the speed of 1.2 meters per second, and every time he walks, x is increasing, which means I can see that walking speed of 1.2 meters per second as the equivalence of dx over dt, like this. Okay, so the next one that I have is going to be this thing right here. We're going to be talking about the time at the instance when he's going to be 3 meters away from the wall, and how far he's away from the wall is denoted by 10 minus x, which means I can write it as 10 minus x equals to 3, which in turn tells me that x will be 7 in that case. So using these, we're supposed to be finding dy over dt. So how are we supposed to be finding it? As you can see, we don't have any equations to differentiate or anything. So let's find something that we can work with first. First thing I notice is that this light is going to be a linear function, and whenever I see a linear function, I see a right angle triangle. That's a big triangle, and that's a small triangle. The beauty is that these guys are going to be similar triangle, and their trigonometric ratios will be equal. So tangent of this big triangle and tangent of this small triangle should be equal, so let's try. Tangent of y over 10 is going to be the tangent of the bigger triangle, and 2 over x will be the smaller triangle. And that's how it should be. Great. So now we have an equation. But before we move on, let's solve for y first. So y equals to 20 over x. That's a little better. So from here, we're going to be putting it through differentiation, and not any kind of differentiation, but we're going to be differentiating it in the term of time, because that's what we want. So we're going to be doing d dt y equals to d dt 20 times x to the power of -1. We're going to keep it like that. And then if we're differentiating y in terms of t, y will be gone and we'll only have 1. But then we'll also have to say that y has been differentiated in terms of t, so we will have dy over dt left. Equals to, we don't touch the constant terms, so 20 is over here, and we're going to be differentiating x in terms of t, which means I'm going to have -1 like this and x to the power of -2. And on top of this, we have to say dx has been differentiated in terms of t, like this. Okay, so we have dy over dt equals to -20 x to the power of -2 dx over dt. And since we want dy over dt and we have all the different values, I guess we can say that we're done. So if we calculate this, our dy over dt will be simply negative 20, and x is 7 to the power of negative 2, dx dt, which is going to be 1.2. So if we see that, negative 20 times 1.2 all over 7 squared, and that's going to be 20% of 20 is going to be 4, so it's going to be negative 24 over 49, and that's going to be my answer. So there you have it. We have successfully solved a related rates problem by differentiating our variables in an implicit way. And with that, I'll conclude today's video, and I hope to see you again next time. Bye bye.